Hello, my name is Elise Tran, and I will be discussing our problem setting. We decided to choose the application area of driverless cars. Advancements in technology have helped to create a more efficient world by allowing people to have increased freedom and independence. Driverless cars would benefit those with disabilities and elderly people who struggle to drive or are unable to drive altogether. These individuals are typically dependent on their family and/or caretakers. With further advancements in this technology, it may be possible to eliminate this dependency. Google and Tesla have already recognized the needs and benefits for this technology and have already begun prototyping and testing. Yet driverless cars remain unperfected. On highways and freeways, driverless cars need to stay within 10% of the speed limit. This can be resolved by checking the speed limit and using a feedback system to adjust accordingly. One of the primary control features of this vehicle is the ability to control the speed and direction of the vehicle. Our goal for this project is to create a control system in order to control the velocity of a vehicle while traveling at highway speeds within 10% of the speed limit. To do so, it will need to receive inputs that tell the car system the speed limit and therefore the speed it should be traveling. In order to determine how well we are controlling our speed, the car will be constantly calculating its speed using its displacement over a specified time interval and adjust the engine force accordingly. By keeping track of and comparing the set allowable speed and the current speed of the car, we will be able to see how well our car is performing. Our success will be measured by analyzing the velocity and percent error.
Hello, my name is Megan Anderson, and today I will be talking to you about the inputs and outputs of our modeled system. We have chosen to use a driverless car as our system. We have determined the inputs of this model to be the force from the car's engine. This force will act upon the mass of the car and will propel it forward, which will produce a velocity as an output. The purpose of this velocity will be to use it later and to monitor it in order to keep the car within 10% of the posted speed limit. On to analysis. In the figure on screen, you can see that we have decided to use the open loop pole locations to analyze our system. This tool has allowed us to easily determine that our system only had one left-hand plane pole, as can be seen in the picture, and is thus stable. In our analysis, we have also found that the car could be disturbed by an incline on the road. From our analysis, we have determined that this disturbance should be modeled as a reference step input. With our system being a type 0, and with our goal of having a finite steady state error, this is the input that we require.
Hello, my name is Madison Lee, and I will be going over the design of our control system and the time domain specifications we want to meet in order to satisfy our control goals. Our closed loop block diagram can be seen here with a controller, a disturbance, and our plant. There is also a sensor which will be giving feedback to our system concerning the output velocity of the closed loop. In order to decide what type of controller we will need for our system, we will be setting some design specifications we would like our system to meet. Our control goal is to maintain the velocity of the car within 10% of the speed limit, and we have chosen the following design specifications to reflect this goal. We would like the output velocity to reach our given input velocity over time with very little error. Therefore, we want our steady-state error to be 0. Ideally, we would like our car to reach full speed reasonably quickly in line with the average car. To achieve this, we have set our rise time for the car to get from 10% of its final speed to 90% of its final speed to be less than 13 seconds. We've also set a settling time of 20 seconds for the car to get within 1% of its final speed. Since one of our time domain specifications is to reduce the steady-state error, we will be implementing a PI, or proportional integral controller. These time domain specifications give rise to the following frequency domain requirements of our closed loop system. The loop gain will contain an integrator, which we can accomplish with the PI controller. We are also going to need an omega crossover at 0.2 radians per second. Our settling time tells us that our phase margin needs to be greater than 30 degrees. In order to decide what controller parameters for KP and KI we will need to achieve these specifications, we are going to analyze our plant in SISO-Tool. Here we can see the Bode plot of the open loop plant, which is stable since our root locus on the right only has poles in the left-hand plane. In the Bodie plots, we can see that we currently have a gain of about -33, which is what we expected since our low frequency term is 1/50, and 20 log 1/50 is about -33 decibels. We're going to raise this to about 24 decibels to make it positive and try to meet our steady state error specification since we need a positive gain. In the new Bodie plot, we can see that we now have a gain of 24 decibels, which now puts our crossover frequency at about 0.5 radians per second and satisfies our time specification. Now we have finally implemented the PI controller by adding an integrator and a 0 before our crossover frequency. Now that we are meeting both our rise time and steady state error specifications with the PI controller, we can record the values for KP and KI that SISO 2 gives us. We're going to use about 300 for KP and 10 for KI to test with our system. Now we can plug these values in for KP and KI back into our closed loop system seen here to be checked in the next step by Zach to see if we need to adjust any of these numbers to improve our system.
Hi, my name is Zach, and I will be talking about the verification, iteration, and robustness analysis portions of our automated car system. We began our verification process by utilizing MATLAB's Simulink program to determine whether or not we had met all of our design specifications. As seen in the block diagram, we simulated a step input that sets our desired speed limit to 30 meters per second, or about 67 miles per hour. This inputs into our forward gain with the PI controller and the plant transfer function. Also notice that the disturbance has been modeled as a reference step input. This is meant to simulate the car moving up a hill. We delayed this disturbance to simulate that we hit a hill sometime during our travel, rather than starting on a hill and remaining on it. The rest of the system is modeled as a closed loop. The plot shown is the output of the Simulink program. This demonstrates the predicted velocity of the car as it gets up to speed, settles, and eventually hits a disturbance, or in this case, the hill. The rise time is about 12.7 seconds, and the settling time sits at about 18 seconds. These meet our goals of 13 seconds and 20 seconds respectively. The disturbance caused by the hill is seen at around 1 minute 40 seconds or 100 seconds. Although it takes the system about 30 seconds to recover, the hill only reduces the car's velocity by about 1.5 meters per second. More importantly, the steady state error of our closed loop system can be seen by looking at the later portion of the plot. The final value rests at about 30 meters per second. This indicates that the steady state error is equal to 0. In reality, this means that our car will stay within the desired 10% of the speed limit. We can verify that the gain and phase are within an acceptable range using the magnitude and phase Bodie plots. To do this, we must calculate the gain and phase margins using the crossover frequency, as well as finding where the phase Bodie plot crosses -180 degrees. Looking at the magnitude plot, we can trace a line from the 0 decibel location to where it meets the plotted line. We can then trace another line down to the x-axis to find the crossover frequency. Here we have measured it to approximately 0.212 radians per second. We can then take this frequency over to the phase Bodie plot to find the angle. This angle is used to then calculate the phase margin. By subtracting it from 180 degrees, we know that our phase margin is approximately 83.3 degrees. We know that the gain margin of this closed loop system is infinite because the phase plot never crosses over -180 degrees. We can safely say that this system is inherently stable because we can set our gain to any value as long as it satisfies the Routh-Hurwitz stability test.
Overall, our system accurately represents the necessary system needed to control the velocity of a driverless car. This system exceeded all of the goals we had set forth early on in the design phase. It is simple, stable, safe, and is able to perform all necessary tasks under the given constraints. This design should hopefully change the accessibility and independence of a disabled person has in being able to get around on their own. We hope you enjoyed this instructional video on creating a control system for the velocity control for a driverless car.